Hello, everyone. Welcome to the Microsoft Research Summit. My name is Josh Benaloh, and I'm a senior cryptographer here at Microsoft Research, and I'm going to be talking about verifiable election technologies and what we're doing with them and how we're using them here at Microsoft. So we have today a crisis of confidence in voting in the United States. We have millions of Americans who do not believe the results of recent elections. And it is a problem. And regardless of one's view of the particular concerns here, there are a few undeniable things that we really do need to acknowledge. And that includes that we are really not providing voters with any substantive evidence that their votes have been correctly counted in an election. Instead, what we ask voters to do is to trust their local election officials, their equipment, the equipment vendors, and the whole chain of custody that is involved in making an election work. That's not to say that there are any problems that we've seen in recent elections. I personally have seen no evidence of any large-scale fraud of any kind, and I'm pretty close to the subject. But it is something that we should be aware of and we should try to do better with. The National Academies of Science, Engineering, and Medicine issued a report 3 years ago that went into a lot of detail on various aspects of the US electoral system. And I'm not going to come close to going into any of the details of most of the report. But one of the findings is that our election systems are today extremely vulnerable. There's a strong recommendation of doing the best we can at applying best practices at improving the system. But this is not enough by itself. And the principal reason for that is we face an asymmetric challenge. Elections in the US are run locally, mostly at the county level, sometimes even the township level. There are only 2 states in the US that administer elections on a statewide level. But the attackers are often much better resourced than the jurisdictions that are managing our elections. The attackers might be nation states or well-funded domestic attackers, and small county governments just aren't equipped to be able to handle a concerted attack from a well-funded adversary. Alex Halderman of the University of Michigan did a lot of work in the Michigan recounts after the 2016 election, and he discovered some glaring vulnerabilities. And he said, I've heard him say this many times, that his undergraduate security class could have changed the results of the 2016 election. And I believe him. Some of the things he's turned up are rather jaw-dropping in what could potentially be done. Now, again, I'm not suggesting there's any evidence that these things have been done, and if they were done, they probably would leave evidence. But still, we don't want them to be done. We want to be able to have better systems. So we should ask ourselves why it is that elections are so much harder. We don't seem to have this problem in other areas. We don't have this problem in banking, it seems. At one time, trust in the banking system was a problem in the US, but now people seem pretty confident that when they put money in a bank, they can get it out anytime they want. Shopping isn't a problem. When people buy things locally online, they seem confident they get what they want or they get it fixed. It's not a problem. Other common areas we don't seem to have this problem with. What is it that makes elections hard? And the principal answer to this is ballot secrecy. If we had to have the same kind of secrecy in banking, for instance, where you couldn't see your bank account, then banking would be a lot harder as well, and other things. So we should talk some about ballot privacy and some of the requirements there, because in a secret ballot election, we certainly want voters to be able to keep their votes private. That we view as a fundamental requirement in elections. But even that isn't enough. It's not enough to just be able to. Voters should also be unable to show anybody else how they voted. They can tell other people how they voted, but they shouldn't be able to give evidence or prove to other people how they voted. If they could sell their votes. They could be subjected to coercion of various kinds. And we don't want this to be a part of our elections. Now, secret ballots were not always a part of elections in the US. In fact, it wasn't until the late 19th century that the secret ballot became used in any large sense in the US. In fact, the 1888 presidential election had so much vote selling and coercion. It was so rife with it that caused the entire country to, in a very short amount of time, sweep in the secret ballot. And by the 1892 presidential election, with the same two candidates facing each other in a secret ballot election, a different candidate won the presidency. So secret ballots are very much an important part of our electoral system. I don't want to give them up, even though they create challenges for us. And one thing we should understand is the secret ballot processes that we've used were a technological advance when they were introduced. We see this today as almost a given. We don't think twice about it. But the idea of being able to vote in a private environment within a public environment where your privacy is being publicly monitored and publicly enforced, this was a technological achievement when it was first developed in the mid-19th century. And it spread around the world somewhat slowly. It took, several decades for it to make it to the US. Now, we really want the kind of transparency that's offered by an open election, an election before the time of secret ballot elections, because with an open ballot election, we can at least see how everybody voted. We can see how our own votes are counted. We know that all the votes are correctly counted. They may have been coerced, but the actual election itself, we might have higher confidence in. So we really want secret ballots for all the reasons I've talked about, but there's a high price that we pay in not being able to as easily audit and be confident in the results. Really, with the current electoral system that we have throughout most of the US, voters can do little more than cast their votes and then hope. It's really not feasible to watch the entire process for any single voter and make sure my vote was properly counted. You can do some things. You can try. A lot of things are done in public view. But even in a low-tech system where you drop your ballot in a ballot box, I know of very few people who will then sit there the entire day and watch that the ballot box is not tampered with, and that at the end of the day, their ballot is counted properly and with all the others. And they would, of course, have to start at the very beginning of the day and see that the ballot box is empty to begin with to have any confidence. So individual verifiability in an election is really not very realistic with the current methods that we're using. Now, we would like to be able to get the transparency that we had in an open ballot election. The question is, what can we do? How close can we come? And it turns out that we can actually come very close. We can do surprisingly well. There are technologies available that allow any inaccuracies and any tampering in an election to be detected. And not just detected, by election officials, but by candidates, by media, by voters themselves. And essentially any observer is able to check and make sure that the votes have been properly counted without any tampering. And when I say without any tampering, I'm not just referring to external tampering. I'm also including internal tampering, internal corruption by election officials or equipment vendors who may have either intentionally or inadvertently left vulnerabilities in their systems. Even forms of tampering that have not yet been thought up. Technologies do exist today that are able to detect any tampering that has happened with the ballots. This set of technologies that achieve this, and it's not just one thing, there are actually multiple ways of doing this, are collectively known as end-to-end verifiability. So an election is end-to-end verifiable if it allows us to trust the accuracy of an election outcome without having to trust the software that may have been used in the system, the hardware, or even the people who are part of running the election. So what is an end-to-end verifiable election? Somewhat more formally, it has two properties. An election is end-to-end verifiable if voters can verify for themselves that their own votes have been correctly recorded, and anyone is able to verify that the recorded votes have been accurately tallied in an election. So this is about the best we can hope to do. You might ask why anyone can't verify that my selections have been accurately recorded, and it's hard to see how we could do that and maintain secrecy. So in some sense, it's up to me as a voter to make sure that my votes have been correctly recorded, although I'll talk more about statistical methods so that we don't have to require all voters to do that. But every voter is in some sense individually responsible. And then anyone can then look at the list of recorded votes and make sure that they've been correctly tallied. So this sounds like a very hard thing to be able to do, but I'll show you right here that it's quite easy to achieve end-to-end verifiability if we have an open election. Now, the modern version of the mid-19th century open election might look like a website where all the votes have been posted. It doesn't even matter how my vote got there anymore, but I can see all the votes have been posted. I can see that my vote is correct. I can see everybody else's vote, and I can see that the votes have been tallied correctly. So achieving the requirements of an end-to-end verifiable election is actually quite easy if we don't have to worry about privacy. And now the question is, can we do this with a secret ballot election? And it turns out the answer is yes, we can. And what we do is take this model and just add a thin layer of encryption at just the right point. So we have the same website showing all of the votes, but this time all the votes are encrypted. So what do we have to do if the votes are encrypted to make this fully end-to-end verifiable? Well, we have to give each voter the capability of checking that the vote recorded by that voter matches that voter's choices. So here, Carol has some way of checking that the encrypted ballot that corresponds to her vote really does capture her correct vote. And we have to do this in a way that doesn't allow her to show anybody else what her vote is. So it's a little tricky, but not as hard as it might seem. The other thing we have to be able to do is show that this set of encrypted ballots corresponds to the announced tally of the election, that there is some mathematical proof which achieves this. And this I'm going to talk about first, actually. So those are the two things we have to do, and that leaves these two questions to be answered. How is it that voters turn their preferences into encrypted votes? And how is it that voters and observers and anybody else can be convinced that the encrypted votes correspond to the tally that's been announced? And for a variety of reasons, I'm going to address the second topic first. It's a little bit more formal, a little bit easier to think about, I think, initially. And chronologically, this is something we understood how to do first. So I'm going to start with that. So to do that, let's first sort of look at what a vote might look like. This might be a representation of a vote where there's just It's very simple. There is one contest on the ballot. There are 4 options. And a valid vote might be a 0 in all but one option. This is saying this voter chose the second candidate or the second choice in this contest. And of course, the voter might choose none of the above, but this is the common simple case. So in tallying an election, we might have the votes of all the voters. And if they're all in this form, tallying an election is nothing more than column-wise addition of these votes. We're just adding up the columns of zeros and ones and nothing more. Really, computing the result of an election is nothing more than basic addition. So we know how to do this. This is pretty easy. The question now is, what happens if these ballots have been encrypted in some way? How can we possibly tally encrypted ballots? So the trick is something that's been around for quite a long time, actually, something known as homomorphic encryption. Homomorphic encryption allows you to do computations on encrypted data without having to decrypt it. You can do meaningful computations on the encrypted data directly in its encrypted form. I want to note something because this sometimes causes some confusion. Many people here may know of homomorphic encryption, may have heard of it. Something called fully homomorphic encryption was developed a little over 10 years ago, and it's become very popular and very well used. Homomorphic encryption, not fully, existed for pretty much as long as public key encryption has existed. The first ideas about homomorphic encryption came about 40 years ago. But basic homomorphic encryption, sometimes called simple or now partial homomorphic encryption, is just a single operation. Fully homomorphic encryption is a very powerful tool that allows you to compute multiple operations, usually addition and multiplication together. And because that's expressively complete, you can do any computation at all with fully homomorphic encryption. The problem is there's a big price to be paid. It's quite inefficient. Simple homomorphic encryption, a single operation, is very, very efficient. And I want to call that distinction just to make sure there's no confusion about that point. Okay, so let's take a look at how encryption typically works. Because with standard encryption, the only thing you ever do with encrypted data is decrypt it eventually. You might encrypt some data and store it and then retrieve it and then decrypt it. You might encrypt some data and then send it to somebody else, and it gets decrypted by the other person. That's a very common use case. But the data itself doesn't change. The encrypted data is static. That's the usual case. If we have homomorphic methods, however, we can apply some operator, and I'm being a little vague here about what the operator might be, but apply an operator to 2 encrypted pieces of data and get a meaningful result. And this process is what's known as homomorphic encryption. So if we have a homomorphic encryption function that computes addition under the covers, then we can do homomorphic tallying of an election. We take the encrypted votes and we combine them with whatever operator it is that does addition under the covers of encryption, and we can produce an encrypted tally. And in most cases, that operation, and in the case I'm going to be talking about, is actual just simple multiplication. If we multiply together these encrypted values, we get an encryption of the sum. And by using that, we can encrypt all of the votes, homomorphically tally them by just multiplying them all together, and we get an encrypted tally. And then we can decrypt just the tally and show everybody that this is a correct decryption of the tally, and people can see, yes, okay, this is the correct decryption of that whole set of recorded votes without having to individually decrypt each of those recorded votes. Okay, so that's the basic idea of homomorphic tallying. The technique that we are using for this is El Gamal encryption. I'm not going to go through this, but it's very standard means of encryption, very old, very common. There's one trick that we're using that's a little bit different because with El-Gamal encryption, if you do pairwise or component-wise multiplication of the encrypted components, you get an encrypted product. Said another way, normally El-Gamal encryption is multiplicatively homomorphic. We want something additively homomorphic. And what we do is just change this to what's sometimes called exponential El-Gamal. And what we encrypt is the data that we're trying to encrypt, but we have that in the exponent. We raise a fixed value to that data power. So the difference is this, g to the m instead of m, which was back there. And by doing that, this changes it so that if we multiply components now, we effectively add the exponents and get an additively homomorphic encryption function. Okay, so El-Gamal encryption has a large number of advantages. One is that it's what's used today for the vast majority of all encrypted web traffic. And most traffic now is encrypted. So it's very, very common, very well known. We have a lot of confidence in the security of El-Gamal. We're not doing something exotic. And it's actually basically just the original Diffie-Hellman key exchange that started public key cryptography in 1976. This even predates the RSA encryption algorithm. So it's very old, very well studied. It provides a natural randomization. It's important that the encryption is randomized because you wouldn't want my encrypted vote and your encrypted vote to be the same if our votes are the same, because then we could tell that the votes were the same. We want every encryption to be different, even if it's an encryption of the same thing. We need to randomize the encryption, and El-Gamal does that very naturally and very easily, although that can be done with other crypto systems. It can be a little bit more awkward. It can be used, as I just described, to get an additive homomorphism. It also supports split key and shared encryption. It's very easy for multiple people to each generate an El-Gamal encryption key and combine them into one El-Gamal public encryption key that can be used to encrypt so that it requires all or a threshold subset of the key holders to be able to work together to decrypt. And you want that in an election because if votes are encrypted, you don't want one person to have the key and be able to decrypt them all. You want to split that power among a canvassing board or some set of entities in opposition that will only work together under the appropriate circumstances to do tallying and other such things. We also want to be able to do certain zero-knowledge proofs of the properties, and El-Gamal encryption is very good at that. There are some very simple zero-knowledge proofs that are well known that can work that to prove that ballots are well formed, for instance. I'll talk about that a little bit more in a bit. And it's extremely efficient. As I said, it's used for most web traffic today, so there's no issue with it being too slow and cumbersome. Okay, that's the first question I promised to answer, but I have to get back to the second question. We know what to do once the votes have been encrypted, but how is it that voters are supposed to turn their preferences into votes, right? We're talking about human beings as voters. How do they encrypt? Well, we don't want them to encrypt with their own devices because their own devices could be compromised. But if we're going to say, okay, you come in, you vote in person using a dedicated device used by the election system, by the election offices, then why is it that I, as a voter, should have any confidence that my selections have been accurately encrypted? So we need to find some way to engage humans in some sort of interactive process so that they can, if they want, check to see that their votes are correctly captured and encrypted. So how is it that humans can do reasonable encryption? It turns out that there are ways of not actually doing the encryption, but checking the encryption that aren't hard at all. And the trick is basically one of being able to believe something even if you haven't seen it in great detail. And I'm going to demonstrate this as a card trick, but this would be done with votes instead. Suppose I have a bunch of cards, and I want to convince you that these cards are all red. Okay, so I make the claim, all of the cards below are red. And now I'll let you challenge me. I'll let you check me. And I'll let you start turning over cards. And you can turn over that one, and maybe you'll choose that one next, and maybe that one next, maybe that one next. And every time you turned over a card, it was red. And you chose which cards to turn over. Well, at this point, there's still one card left that hasn't been turned over. But you now have some reason to believe that this remaining card is red, because you got to choose which card stayed uncovered, and anytime you turned over a card, it was red. So the only way that that card might be black would be if somehow I was able to guess in advance what you were going to do and which cards you were going to turn over. Furthermore, this card is a card that you haven't seen. So you have developed some belief that this card is red, even though you haven't turned it over, you don't know what it is. You don't know, even though you know that it's red or you believe it's red, you have no idea whether it's a diamond or a heart. You don't know what its rank is. So you have no way, once this process is done, of going away and convincing anybody that that card is red. You believe the card is red because you engaged in this process, but you have no way of showing anybody what your vote was if that card represents your vote. You have good reason to believe it's red, but it's non-transferable. Even though you now believe it's red, there's nothing you can do to go and convince somebody else after the fact that that card is red. So that card could represent your vote. You could think of yourself as writing your name on that card, and it becomes your vote. Okay, so now let's turn this more a little bit to voting. Suppose I, as a voter, have said, I want to vote for Adams, and the device says, okay, here are a bunch of votes for Adams. They're all encrypted, and the voter can say, okay, I'm going to take that fourth one and say, device, decrypt, reveal the keys, decrypt the other ones. Now, voters do not have to do decryption or check decryption or do anything with numbers in practice. This is just getting a little bit closer to what would actually happen. And then this decryption could be done to show voters that the votes that they asked to be revealed are all for Adams. Therefore, again, they have reason to believe that this last one is for Adams. Now, in practice, we wouldn't ask voters to do anything like this. The only thing we need to do in practice is to give voters an opportunity to open a ballot whenever they want during the process of creating a vote and casting a vote. Once the vote is cast, it's locked. But they can say, okay, here's the vote I want. Create an encrypted version of that for me. Of course, we wouldn't use encryption as the term in talking to voters, but we would give voters effectively a confirmation, a commitment to that vote, the encryption of that vote, and then give the voters the ability to either cast it or choose to spoil it, and spoiling it will cause it to be opened. Now, not every voter needs to do this. Even if just a very small fraction of voters spoil even just a single ballot, you get very high integrity. Statistics are on our side here. For instance, if 100 voters in a national election each spoil one single ballot, then any alteration of 1% or more of the votes in the entire election would be likely to be detected, would probably be detected, as long as this is reasonably random. Nobody knows which voters might spoil a ballot ahead of time. Or we could turn that up a little bit and imagine 1% of voters in an election spoiling ballots. Not everybody, not close to everybody, just a tiny fraction, just 1%. That's enough to get the confidence in an election down to within 100 votes. In an election, a national election, which might have well over 100 million votes, being able to be accurate within 100 votes is a very strong capability. And it doesn't take much. Just a small fraction of voters need to do the spoiling and checking in order to achieve that. So what does an election look like in practice? Well, when it's done, there will be a record. You will have all the ballots that have been cast. You'll have the totals together with the proof. You'll have all the spoiled ballots and decryptions of all the spoiled ballots. So if I am a diligent voter, I might spoil a ballot and then look at the website afterwards and check my spoiled ballot and see that it decrypted the way I expected it to. I still don't have to decrypt. I just would be able to look and see, okay, this supposedly was decrypted the way that I had expected. And the other things that would be there would be the proofs, which you might remember done with homomorphic tallying. But of course, we get the sum effectively by taking the product of these votes, and then we can keep everything else encrypted, and then just release a key to show that this has been decrypted properly. So all of these things are easily checkable. Anybody can write some sort of a verification tool that will go through and check all of these things and make sure that everything on the website is correct. So voters don't have to be burdened with doing any encryptions or decryptions of any kind. They can just look at the website and see that their votes are there, recorded the way they expected. They're cast, if they, presumably they cast one ballot each and make sure that the cast ballot is part of the record. And if they spoiled any ballots, they can make sure the spoiled ballots are part of the record and that they are shown as having decrypted the way that they expect. Okay, so this leaves a very nice task that's completely separate from what a voter would be likely to do, which is writing a verifier that'll go through the election record. And there are a lot of things that a verifier has to be able to do. The verification app would verify that all of the encrypted ballots are correctly combined to form the encrypted tallies, to verify that the encrypted tally is correctly decrypted, to verify that all the spoiled ballots are correctly decrypted, and to verify that each encrypted ballot is well formed, meaning that it really is just encryptions of zeros and ones, and this is where most of the zero knowledge proofs come in. So while possible, I've worked with students at several places and had them write election verifiers of this sort. It's a wonderful little project. I'll talk about that a little bit more in a bit. But first, I just want to give you a sense of what this looks like to a voter. A verifiable election system to a voter can look exactly like a current system with one small addition, and that is we would give the voter a receipt of some sort, a confirmation code basically, which looks like here is not your vote. This doesn't show how you voted, but this is the encrypted vote or a hash of your encrypted vote, some commitment to your encrypted vote. So you can take this home and check on the website. Yep, my encrypted vote is there. And you can also have one of these for every time you spoiled a ballot and say, yep, my spoiled ballot is there. And that looks correct. That's the only difference. Now, I've learned in my years of working in this subject that I can give voters options. I can give them something like this and give them the option to do extra, but I can't get in their way and force them to do anything more. So voters can take these receipts, check that their votes have been properly recorded, and we found that when this is done, a good percentage, maybe 30% of voters will do this. Most voters will throw their receipts away. They'll look at this and say, what is this? I don't want it. Throw it away. That's fine. We don't need every voter to check. Any voter who wants to can check. That's the thing we're achieving. Voters could also write their own election verifiers if they want to. Very few probably will, but it's not that hard. It's a nice class project. Or they could download verifiers from sources of their choice and run them on any particular election. So from their favorite source, from their maybe my niece just took a computer science class where she wrote an election verifier. Great, I'll take that and I'll run that on my election and see. Or maybe my candidate has a verifier posted that I can do. Or I could, as a voter, just believe the verifications done by political parties or various interest groups or observers, in any third party can run their own verifier and check. Or I can do what most people still do today, is just accept the results. I don't have to do any of these things. It's a capability, it's not a requirement. Okay, so where are we with these technologies? Well, I'll quickly mention that there have been some real-world deployments. Helios is a system that uses this technology in an entirely web-based form, entirely online. It's been used for many different applications. It was used to elect the president of UC Louvain in Belgium, not the student body president, the actual president of the university. It's been used by Princeton University for student government elections, various professional societies. It's a convenient tool for a web-based form. I wouldn't recommend this for public elections, but for smaller society elections, things like that, I think that's a very good approach. There's a system called Scantegrity that was used about a decade ago in municipal elections in Tacoma Park, Maryland. It had some very interesting tricks to it. But what I'm going to be talking about mostly now for the last few minutes of this presentation is ElectionGuard. This is something that Microsoft has put together. It's a free open source toolkit. It's not an entire election system, but it's a toolkit that enables others to take these tools and build them into other systems, touchscreen systems, optical scanners, vote-by-mail systems, and even internet voting if you want to do that, although again, I'm not recommending that for public elections. This is something that Microsoft is making available free. It's sort of a corporate responsibility because we have the expertise to do this, and it is very technical, and frankly, current election vendors are not very well resourced in the US and don't have the skills to be able to do something like this, but they can take what we provide and build it into their systems. Now, just because we build it doesn't mean you have to trust us either. The idea of this end-to-end verifiability is you don't have to trust anybody, including Microsoft, in using this, and you can check for yourself. So we've had various partners that we've been working with and various jurisdictions that have been very interested in using this to build ElectionGuard, to start making it available. In particular, it got its first public use in Fulton, Wisconsin, about 18 months ago. This was going to be the first of many uses at the time, but note the date, February 2020. Some things started to happen in March 2020. Things kind of shut down. And a lot of election administrators we were talking to who were very interested in trying things and innovating turned from a posture of innovation to a posture of hanging on by their fingernails and just trying to make sure our elections happened at all that year. So we didn't get many opportunities to do pilots, but we are starting that up again, and that is starting to happen. It did get a lot of coverage at the time. Various sources, CNN had some nice coverage, USA Today. I particularly like CNET's claim about this, that this could be the most important product from Microsoft in 2020 if it works. Yes, it works. It really does work. Another use in the November 2020 elections was used in a very different form for preserving privacy in a post-election risk-limiting audit that happened after the November 2020 elections. It was done in one county in California. Went very well. Another place that it was used, this may be somewhat surprising, is in the U.S. House of Representatives Democratic Caucus. We, of course, made this available to both House and Senate and all the caucuses, but the most elections in Congress are open ballot. But the elections for the leadership are secret ballot, even within the caucus. And they didn't want to meet in person. So we had another partner, Markup in this case, who we worked with to build an app for use in this context. And this was used to elect the speaker and the whip and majority leader and other offices. Went very well. This is not a fully public election. It was very constrained, so we felt comfortable with this application, but it was something that we're proud of it having been done. And just a few months ago, we announced a partnership with one of the major election vendors in the US, Hart and Civic, and they will be integrating this technology into their premier line of optical scanners. So maybe in a few years coming to a voting system near you. We're certainly talking to other vendors as well. We hope it will become ubiquitous, but in particular, Hart is doing this, and we're expecting to see some pilots early next year. Just a couple of things about ElectionGuard. We've worked hard to make it very clean, very simple AI, try to make it hard to misuse. And my key design criterion in a lot of the choices was trying to make the writing of election verifiers as easy as possible, because this is something we want many people to do. We want independent verification. A Microsoft verifier on Microsoft ElectionGuard isn't so useful. We want you and your students and others to write verifiers to check elections that have used this technology. So writing an election verifier is a great class opportunity. It's a great independent study project, or even an in-class assignment. And please feel free to contact me if you want to learn more. Also, everything is open source, so we welcome contributions. We'd be very happy to have work done. There's a lot that's being built out and extended, and the more the merrier. This is a project that we'd like to have many, many people be part of in improving election confidence. Some references, electionguard.vote is the main site, and all of the open source stuff is on GitHub at github.com, Microsoft ElectionGuard. That's going to wrap things up. I thank you for your time and attention. For those of you in the Pacific time zone, I will be sticking around a little bit after. The talk immediately after this is going to be by Dan Wallach of Rice University. He's going to be talking about how he's developed this technology as a teaching tool and built a small unit for a security class that uses this technology. So please, I encourage you to stay around for that. And then immediately afterwards, for those in the Pacific time zone, both Dan and I will be available for questions, and we'd be happy to answer any questions that you might have. So thank you for joining us, and I hope to hear from you soon. You can contact me personally at benaloh@microsoft.com. Thank you again.
Hello, everybody, and welcome back to the Microsoft Research Summit 2021. My name is Dan Wallach. I'm a professor at Rice University, and today I'm going to be telling you about some work I'm doing in collaboration with Microsoft on a system called ElectionGuard, and where it is and where it's going. And first, I'm going to make sure I click in the right window so that way my slides work. So my research is in the space of electronic voting system security. That has meant finding vulnerabilities in older systems, as well as designing processes, procedures, and designs for new systems that generally involve printed paper ballots. Now, I have been working in this area on and off for almost 20 years, and the more I learn about it, the harder I realize it is to build secure, usable, reliable, well-engineered voting systems. And it's important to also learn lessons from other people who have had troubles. This is an example where Swiss Post, the post office of Switzerland, commissioned a company to build for them a fancy cryptographic online voting system. And it turned out to have really significant bugs that would allow somebody to create forged proofs. So the proof is claiming that some property is true of an encrypted value, and turns out you can forge the proofs. That's really bad. In the end, to Swiss Post's credit, they pulled the trial that they were doing and said, wow, we need to get back and really think about what we're doing. So with that as a backdrop, Microsoft is now also working in this space. So the talk before me, you heard from Josh Benaloh, who did a lot of the design work, all of the design work behind ElectionGuard. And Microsoft's goal was to produce an open source software development kit that would enable other vendors and companies to build secure electronic voting machines using state-of-the-art cryptography, and would take a lot of the design and engineering research and development risk out of it. Rather than having to figure out how to do it yourself where you might get it wrong, we're going to have really good people designing something right and getting it right from the beginning. And that's what ElectionGuard was meant to be. The original implementation was, again, designed by Josh Benaloh and implemented at Galois Research in Portland, Oregon. They built a formal model that allowed them just to explore the design and make sure it fit together. They built a voting machine client that was in C, and they built a verifier in Rust. That C code was then embedded alongside a ballot marking device that was done by a not-for-profit called VotingWorks, and that was piloted in an election in early 2020 in Fulton, Wisconsin. I hope I got that pointing at the correct part of the map. It was a very small pilot, but nonetheless an important opportunity to validate that all of these things work. Now, when I was getting engaged in the project was in 2020 that things were in motion. There were many changes to the spec. There was a new contractor working on it, Inferno Red, and I was on sabbatical from Rice working with VotingWorks. And the project that I was going to build was an election auditing technique, which I'll tell you about in a couple slides. But I needed all the same cryptographic primitives. I needed all the machinery that was in ElectionGuard, the voting machine, I needed in the thing that we were building, an election auditing tool. And I didn't want to start from scratch. Who does? So there was very quickly, I'm in meetings with Microsoft people and others, and there was a collective decision that we were going to start over. And it was going to be in Python, and there would be a full-featured Python reference implementation where everything is there, everything works, everything is tested, etc. And then there would be offshoot implementations that would implement subsets of the reference implementation that would be useful for specific use cases where maybe you couldn't fit Python. But Python was going to be the reference implementation. And at the time, other people were busy, and I needed it, so I started working on it, and later on handed it off to the team at Inferno Red. So where do we stand today, which is a year and a half after that? Well, now we have really extensive unit tests. This code is not what I would call formally verified, but it is based on some battle-hardened math with tests that try lots and lots of inputs looking for counterexamples. And what that means is, even though these tests are not the same thing as formal verification, nonetheless, they have helped us find bugs in the spec. Where there was like a typo in an equation, well, then the tests didn't pass. So that's all done. Also, this is built in modern Python 3 with type annotations, which means that we can type check it. And that means that a whole class of runtime bugs that happen in dynamically typed programming languages, none of those bugs should manifest themselves in the ElectionGuard reference implementation. The code is pretty good stuff. It's written in a mostly functional, simplified subset of Python, limited use of exceptions, and by doing this, it's relatively easy to cut and paste the Python into some other programming language that you prefer, because if you have functions and if you have data structures, then you can implement ElectionGuard by transliterating the code from Python to your favorite programming language. And from the beginning, we knew that parallelization was going to be an important attribute. And that by thinking about that at the start, it really helped us later on when we needed to get scalable performance. That's also coming up in a future slide. Not only do we need to have all of the cryptographic machinery, but we need to have data structures that represent what is an election, what is a contest, what is a candidate, Well, how many candidates are in a contest? Is it a contest where you can vote for one of N or K of N or something else? So ElectionGuard has a full suite of data structures to represent elections, contests, ballots, encrypted ballots, and many other related things, all built around some data structures that were designed at the National Institute of Standards and Technologies for precisely this sort of thing. And that means that we can serialize these Python data structures out to JSON, and then now we have an interchange format that we can have be portable from Python to other implementations. So in order to tell you about the thing that I built, I have to first have a brief digression, and I need to tell you a little bit about something called a risk limiting audit. So this is a process that happens after an election is over. And what we're trying to do is to look at hand-marked paper ballots and electronic tallies of those paper ballots. And we're worried that the computer that does the electronic tallying might be mistaken or perhaps tampered or hacked. So computers can count really fast, but we're worried about their security. Physical paper is very secure, but it's very slow. It requires human beings to move it around. So what we want is a statistical sampling methodology that lets us roll dice to pick out which ballots we're going to look at, to touch just a small number of ballots and match them up one-to-one with the electronic version. And that helps us gain confidence that any error in the electronic tabulation is too small to change the winner. So that's the risk that we're trying to limit in a risk limiting audit. We're trying to limit the risk of having the wrong winner of an election. This is a statistical method that was designed about a decade ago by a professor in the stats department at UC Berkeley, and it's growing in use across the country. So what we're doing is a real-world physical process to mitigate against the risks of software that either has bugs or is tampered. So how can we use some of this cryptographic machinery that's in ElectionGuard to improve a risk-limiting audit, which is a physical real-world process? So first, I have to tell you about one little corner case about risk-limiting audits, which is that the number of ballots you're supposed to look at is a function of the margin of victory. If the margin of victory in an election gets really small, you need to look at more ballots because the margin of error, or your tolerance, your risk for error is much smaller without changing who won when you have a small margin of victory. So how do we compute that? Well, we ask the computer to tell us the margin of victory. What if that's the very computer that we're trying to audit? What if it's lying? So cryptography to the rescue. If we can encrypt the entire election, encrypt all the ballots, and post those encrypted ballots online prior to the start of the risk-limiting audit, then that means that any funny business where there might have been, where the machine that's doing the tallying might have been trying to manipulate the outcome, once it's committed to all those encrypted ballots, it can't take them back. And from the encrypted ballots, using all the same mathematics of ElectionGuard, any independent observer can verify that this set of encrypted ballots implies this margin of victory. And by taking that out of the hands of the vote tallying computers, we improve the security of the risk-limiting audit. These ideas were first explored in a research paper only in 2019. So here I am, 1 year after the publication of this paper, trying to implement this idea. But before I can implement the idea, I have to make ElectionGuard go fast. Because here are some rough numbers. Take a big city the size of Houston, Texas. In a major national election, we could easily have 1.2 million ballots. And pretend that those all went through a high-speed paper scanner, and now I have a comma-separated value file with 1.2 million rows, and that's my input. That's where I'm starting a computation. I need to encrypt each of those, and every ballot, by the way, will generate about a megabyte of ciphertext. So now I need to generate a terabyte of data. And If I was running on a single core of my desktop, it would take 6 seconds per ballot times 1.2 million ballots. It's not going to happen. So we need to go at 160 ballots per second in order to encrypt the election in about 2 hours. The only way we're going to do that is to throw somewhere north of 1,000 CPU cores at the problem. So one of the nice parts about ElectionGuard is all of the core abstractions. Here is a plain text ballot encrypted. Can be easily parallelized. Here are 1 million ballots, encrypt them independently. So when you look at the problem that way, this maps very, very well to a MapReduce style computation, where you're mapping from plain text ballots to encrypted ballots, and then the reduction is where you are doing a homomorphic tally of encrypted ballots. You can add ciphertexts without decrypting them first. We can do this homomorphic tally. That looks like the reduction part of a MapReduce computation. So this is a style of parallelizing programs that we have been familiar with since the early 2000s. It's well understood, and it works really well. At the end, now we have 1,000 machines, perhaps on Amazon EC2, perhaps on Microsoft Azure, writing out to some kind of parallel file storage system like Amazon S3 or Azure Blob Storage. And these can be written concurrently from thousands of separate computers. And at the very end, the election official just computes a Merkle tree over all of these files and publishes one root hash. So in fact, this was what I wrote for my sabbatical in the calendar year of 2020. VotingWorks is a work-from-home company, so I was working from home for VotingWorks while I was on sabbatical. Then COVID happened, and I continued working from home, except suddenly I had housemates again. But anyway, so this went from idea to pilot implementation in less than a year. And so we did our pilot with the election officials at Inyo County, California, which I've highlighted on the map on the right. And, I engineered the system for 1.2 million ballots and ran it with just shy of 10,000. So this happened fast, like 3 minutes flat to encrypt everything. And that was the world's first ever verifiable risk limiting audit. Yay. Trumpets, fanfare. It was pretty cool. And all the code is open source. You can download it all today. So the next thing I want to talk about, marching along with my talk, is a more recent thing that I built. I was talking to some people at Microsoft, and I said, wouldn't it be cool if we could use ElectionGuard to help teach these concepts of encryption and whatnot to computer science students at universities? And so I spent a month this summer in 2021 building this. The goal is to have a 2 or 3 week long assignment. This could fit into a cryptography class. This could fit into a computer security class that might have a cryptography module of some sort. And the ElectionGuard, building ElectionGuard teaches you a lot of the pieces and parts of how many other cryptographic systems work. So it seems like a good place to begin. If you want to understand more sophisticated hash data structures, ElectionGuard uses simple ones. If you want to understand more sophisticated zero-knowledge proofs, ElectionGuard uses simpler ones. It's a good place to begin. So what did I build? I built 2 separate implementations of exactly the same thing. So these are called ElectionGuard EDU Kotlin and Python, implemented respectively in the programming languages Kotlin and Python. And there's complete feature parity. All the functions have the same names, all the functions do the same things, and the idea is that all the code is there, but there are holes. There are functions that say to do. They're not done yet. And it's up to the student to fill in those blanks. And I used all of the original ElectionGuard unit tests as an autograder, just assign points to them to make sure that students implement the functions that cause the tests to pass. Here's the assignment. In week 1, they implement a variety of, let's call them missing functions. So one is using elgamal in a mode where you have multiple trustees who combine their public keys together to create a shared public key, where somebody can encrypt a message for the shared key, and then all of those trustees must work together to decrypt that message. We're using partial decryption and then combination. A fairly sophisticated topic, although the ElectionGuard math is just a bunch of multiplies. It's very simple. So that's just one of these missing functions that students have to put together. Likewise, they use encryption primitives, including the ElectionGuard encryption and Chomsky-Peterson non-interactive zero-knowledge proofs, to encrypt an individual counter. A ballot is a set of races, a race is a set of candidates, and for each candidate, there is a little counter that's a 0 or a 1. So they implement that in the first week, as well as I have them implement a test where if you tamper with the ciphertext, then the Chomsky-Peterson proof breaks. But that's a property that you would expect to be true. They're going to verify that property. In week 2, the students put it all together for general purpose, vote for any K out of N candidate style elections. And so ElectionGuard has a particular spec for how you're supposed to encrypt this, how you're supposed to use placeholders, what kinds of properties you're proving, and what kinds of properties you're checking. So week 1, the students are getting used to the library. Week 2, they're implementing the real deal for how you encrypt a ballot. And they're also doing some performance measurement. Since performance matters, students should have to think about and measure some performance. I also wrote up an optional week 3 where the way ElectionGuard does its modular exponentiation, which is the core primitive inside ElectionGuard, the core primitive inside Chomsky-Peterson proofs, oftentimes you have the same value, either a generator or a public key that's a value being used as the base and then taken to some modular exponent. There are some really simple performance optimizations you can do where you do some pre-computation in advance, and then you can replace that modular exponentiation with a series of lookups and multiplies. So the students, as an optional third week exercise, could implement that. Here's a fun thing I did that any student using this as an exercise will hopefully appreciate. So there's some code on the right that hopefully is very simple. We start with a random key pair, and we use the key pair to encrypt the number 3, and then we decrypt the number, we decrypt that ciphertext using the key pair, and we get back out the plain text. So we can see that here it is Kotlin telling us that the plain text is 3 again. But if I say print the ciphertext, I get this big, long mess of digits. And if some of the units tests don't pass, a student will look at a 4,000-bit number and not really know where to begin to debug it. And that's not fun if you're a student. It's also not fun if you are a professor on sabbatical trying to do the very same thing. So for the ElectionGuard EDU codebase, I added symbolic formulas. Whenever you take two numbers and multiply them or exponentiate them or add them or do whatever you do, you are building a symbolic expression as you go. So if I look at that thing where I say, show me the formula for the pad portion of the ciphertext, that's an infix expression. That's just g to the r for some random value r. If I look at that part, well, it looks the same as before, but I know where that came from. I know that that's actually the public key. There's actually a way inside the library to change what the label is. So I could change this formula to replace it with, just the string public-key. We could do this in a bunch of ways. But this, I can then look at this whole thing and say, oh, right, that looks like g cubed. That's the part on the top line. And then the part on the bottom line looks like g to the a to the r. I mean, if you're not a Lisp programmer, then prefix notation like this is not the world's easiest thing to read. But I promise you, if you are a student trying to debug this code, this will make your life much, much easier. So The last thing I wanted to mention is that this is built to be an assignment working with GitHub Classroom and using GitHub Actions to run the autograder. So every time a student does a git commit, git push, the autograder runs as a push action inside the GitHub cloud somewhere. So the way that works is that it's simply the unit tests are mapped to points, and the autograder just runs the unit tests and assigns points to them and prints at the bottom. So here we see our student starting off with 0 out of 19 points, and it says the names of all the unit tests that have failed. When they eventually get to the full set of points, then the build will pass as well, and when they look at their GitHub commit history, they'll see red X's up until the point where they got the build working, and then they'll see a green check mark. So this is great for the students because they're not reliant on their personal computer. If something goes wrong, if their computer is configured in a weird way, and if you've ever taught a large class, you know that there's always 1 or 2 students who have computers that somehow got into a strange state. Now the student will have confidence that when they push the code and the tests pass on the server, that they're good. They didn't forget anything. There's nothing weird about their computer. If it works on the server, it works. From a grader's perspective, this is also great because now the graders don't need to download the code. The grader just looks at what's on GitHub, including the code that's submitted and the unit tests that have passed or failed. And this really speeds up the effort for your lab assistants and teaching assistants to assign grades to students using this material. All right, so that's all available. If you want to use it, you email me and say, "Hi, Dan, I would love to teach with your materials." And then I will give you access to 2 private repositories that have 2 branches. Here's the branch that you hand out to the students, and here's the branch that has a reference implementation where all the tests pass. So that way you can, have something to look at, something to see how it's all supposed to fit together for yourself. The Python and Kotlin code is absolutely equivalent. The assignment spec is 1 LaTeX file that just has little if-defs inside of it, so it can generate a handout for Python and a handout for Kotlin, exactly the same. So it's just a matter of if you think that your students have had good Python skills, then use the Python version of the assignment. If you think your students know Kotlin, then use the Kotlin version. If your students know Java, Kotlin is probably easier to pick up than Python. It's up to you, but I'm giving you 2 completely separate implementations that work exactly the same way. If you're not sure, if you want to learn more, this URL below will give you access to a public repository where you can see my slide deck that introduces modern cryptography for certain definitions of modern that other people might disagree with, but enough cryptography to be able to do the assignment, as well as some handout PDFs so you can see what it looks like from a student's perspective. All right, in the last couple minutes left, I want to mention that ElectionGuard implementations are happening completely outside of Microsoft, outside of me, outside of Inferno Red. So there are 2 open source ones that I've found so far. One was built by a fellow named John Caron, and he re-implemented it from Python into Java. Another fellow, Alex Mason, built it in Haskell. I think this is sort of proof that we kept the code simple enough that people could look at it and transliterate it to their favorite programming language. So if you are an aficionado of Haskell, you can use that. Here's a recent paper that I was thrilled to see published. So, I said that we haven't done any machine-checked proofs, but somebody else did on their own. So here we have 3 authors who put in a bunch of effort and did a machine-checked proof of universal verifiability. What's that? It's one of many properties that you might want from an election system. And so they implemented this in a formal way, which I think is fantastic, good stuff. This is further evidence that ElectionGuard is becoming a platform for building other applications, a platform for launching other research efforts. So in my final slide for today, I'm going to tell you a little bit about some ongoing work. Microsoft itself has partnered with Hart InterCivic, which is one of the 3 big US-based election equipment providers. There isn't much more that's available in public right now, but I really look forward to seeing what comes out of this. I think this is a test about whether ElectionGuard really is the right level of abstraction for a company to adopt without having to have a deep level of technical sophistication for how this sort of election-related cryptography works. I hope that this goes well. Meanwhile, at Rice, I happen to be running a senior-level design class this semester, and I have a team of 6 students working on integrating ElectionGuard with a vote-by-mail style system. The idea being that there would be an in-browser experience to pick who you're voting for, and it would generate a printed ballot that would have some cryptographic add-ons at the bottom, but would otherwise be a completely ordinary paper ballot. This is work in progress, and it's going to involve making a TypeScript reimplementation of ElectionGuard, which again should be fairly straightforward and useful to have around. And the last thing is that I'm currently working with both Josh Benaloh at Microsoft Research and Olivier Perea at Université Catholique Louvain-la-Neuve in Belgium. And we are going back and forth with ideas for how to make ElectionGuard go faster. In particular, how to make the cryptography go faster. It turns out when you're doing the same thing over and over again, there are lots of opportunities for performance enhancements. So that's what we're working on. I'd like to thank you all very much for coming to my talk, and everybody have a great day. Thank you very much.
Enjoyed the recorded presentations that just aired. Dan Wallach and I are here live. Josh Benaloh, and we're hoping to be able to take any questions that you might have here live. Dan?
Hi, so I'm Dan Wallach, and thank you again for having me here at the Microsoft Research Summit. Again, we are live to take your questions, and I'm going to start off by asking Josh about a question from the chat during the talk, which is that we've chosen to use El Gamal cryptography, which is a classic from the early 80s, along with much of my favorite music. And these days, we're worried about post-quantum. We're worried about computers that might be able to break the public key cryptography that's used in El Gamal and other crypto systems. So what would it take to re-engineer ElectionGuard to use a post-quantum crypto system? What would be the costs? What would it be, in terms of size of ballot, performance, and so forth?
Thanks, Dan. And we considered this quite a lot during the development of ElectionGuard. And the truth is that post-quantum algorithms are just not yet up to the requirements that we have. We have many challenges that we've had to overcome, and we are stuck with the current class of algorithms now for a variety of reasons. First of all, performance. The quantum-resistant algorithms that are just being developed now have huge issues with performance in one dimension or another. Either they're very slow, they have enormously large keys, enormously large ciphertext, many things that would make a post-quantum solution just impractical for ElectionGuard today. Another issue is that we've tried very hard to make ElectionGuard very much easily accessible, to have good understandability by anybody who's writing a verifier. So we could make things a little bit more performant by using elliptic key cryptography, but instead we're using simple integer algorithms. We're using 4096-bit El Gamal, which is much larger than you would normally see, but that's giving us a good margin of error while keeping things easily understandable. And we have, I mentioned in the talk, several of the advantages of El Gamal being very good for split key, being very good for having zero knowledge proofs of the capabilities. Those things just aren't there yet with the post-quantum algorithms that exist. So if in several years we get to a point where we might want to do a post-quantum version of ElectionGuard, or you might want to do it because it's all open source after all, feel free, please, then we'll cross that bridge when we come to it. Right now, the threat is pretty minimal because if somebody 20 years from now actually came up with a suitable quantum computer that could break 4096-bit encryption, and once they got tired of applying that to steal all the Bitcoin in the world and the other things that they might do with it, and they turned it to an election record from 20 years earlier, what they would get is, here are a bunch of clear text votes, but they still wouldn't be able to see who it is that cast those votes. And the only link would be something of the sort of, if I had saved my verification code from 20 years ago and somebody could look at that code, they could associate that in the record and say, that code, that 20-year-old code is associated with that vote. And that, it's a threat, but I think it's a threat that we can manage. So I'm not that worried about that.
And when you talk to the political scientists, they say, tell me your address and I'll tell you how you vote. The homogeneity of neighborhoods tells you with high probability how anybody who lives in those neighborhoods vote. So you actually have the sophistication of the cryptography is far greater than the sophistication of how we self-sort ourselves into where we choose to live and work.
Indeed. So again, we encourage people to type any questions they may have in the chat. I'm not seeing any others yet, but please feel free.
So while we're waiting, let me throw a question at you, Josh.
Please.
This is like, I have my own personal cryptographer. I can ask him anything I want. What a great opportunity. So we hear a lot about blockchain, internet voting, and often blockchain internet voting, and sometimes that's pronounced mobile voting, because if it's on your phone, that's somehow different from in your web browser. How are the technologies that we're using in ElectionGuard or related technologies from the blockchain community, what problems do they solve and what problems do they not solve? Like, what are the risks or benefits or dangers of blockchain/internet voting?
Well, because I'm about to say some very negative things, I should qualify this by saying I'm not anti-blockchain. Blockchains are okay. They do interesting things. They should do those interesting things as far away from elections as possible. I was quoted by the Associated Press a few years ago saying that anyone promoting blockchain elections either doesn't understand blockchains, doesn't understand elections, or is being dishonest. And I stand by that quote. Blockchains don't solve any of the real problems associated with internet voting. And there are some real problems associated with internet voting. And in fact, the use of blockchains just creates new problems and makes things harder. So I'm not going to go into it in great gory detail, but there are so many problems introduced by blockchains, and they just, excuse me, don't solve any of the real problems. They don't solve, for instance, the client malware problem. If I'm voting over the internet and there's malware on my device that flips my vote, then that's before it ever touches a blockchain. My vote is changed. Now, end-to-end verifiability, this technology can be used to make it possible for me to see that my vote has been flipped. And if I check it, I can see that, and I can then go somewhere else and correct it, because there's malware, obviously malware on my device that did it. I could go to another place. So I can address these issues, but they still create a lot of challenges. And the short of this is that although there are many people who would really love to do internet voting, and many reasons why people seem to want to do internet voting, even though it doesn't seem to have the desired effect on turnout that one might expect, doesn't have, people suggest that if we have internet voting, then we'll have a tremendous increase in voter turnout. In the cases where it's been available, that just doesn't seem to be the case. But even with all those things, we don't seem to be ready to do responsible internet voting in public elections today. There are narrow contexts where internet voting can make sense, certainly for things like professional societies or student body elections, things which are a little bit less sensitive. It's a very good use of the technology and very good use of end-to-end verifiability. But for general public elections today, the general consensus is that we're not quite ready.
So I think an interesting related case is that members of the US military who are serving abroad will, and I'm not making this up, fax their ballots back. And
Yes.
if the competition is, can you do something better than a fax machine, where an election official, or where a Pentagon official somewhere in Washington, D.C. receives tens of thousands of faxes and then transcribes them back onto ballots and then mails those back, that's something we can probably do better than.
Yeah, I agree with that. Ironically, faxes used to be more secure than they are today. They used to go over at least a private dedicated line. It's kind of hard to tap a fax channel, except faxes today typically travel over the internet and not over secure channels. In fact, what we're seeing some of today is people returning ballots by email as email attachments, which is kind of the worst that you could imagine here. And we can certainly have better solutions than that. Email attachments have sort of all the tamperability that one might imagine. And then even beyond that, I've talked to local election officials who say, I get email attachments as ballots, and I'm supposed to have my staff click on these random attachments and open them. This is risking infecting their machines. So email is about the worst thing we can do. There are better things. There's a system called Helios voting that is an internet version of end-to-end verifiability. It was deployed about 10 years ago. It's been used to cast millions of votes, and I think it's a very good solution for low coercion, low risk elections like student body elections, like professional societies. It's been used a lot there. It's great for that. I don't think we're ready for it for internet voting, but for public elections. But it's a lot better than email attachments. I'll certainly say that.
So I want to go to a question from Robert Sim, who asks, what's your biggest challenge in describing this technology to election officials, and what are the barriers to adoption? Both Josh and I have been working on some version of this problem for a long, long time. And in fact, an earlier collaboration where Josh and I were working together with an election official in Austin, Texas, or the Travis County Clerk's office, they got excited about this class of technology as applied to voting in the early 2010s and pointed the finger at us and said, hey, you, time to stop criticizing us and time to get in the room and help. And we ended up designing a system called StarVote. And for boring bureaucratic reasons, the procurement process didn't quite work out. And ElectionGuard is in many respects that idea resurrected and made better. And so in some cases, election officials get this and come to us. In other cases, yeah, we have to sell this to election officials. And election officials, turns out, are super chatty with each other. They have conferences, in pre-COVID, they traveled all over the place to go see each other and hang out. And that's how ideas spread in that community. And I think that one of the things that I like about the ElectionGuard project is that by Microsoft partnering with election equipment vendors, that helps get these technologies closer to election officials, where when their own vendor is offering it as an option, they might be more willing to consider it.
Yeah, and Robert, you've certainly hit on an important issue here. One of the big challenges is what's sometimes called arithmophobia, fear of math. I have spoken to election officials who have said, this end-to-end verifiability you're talking about, it sounds really good. The idea of not having to trust me, not having to trust my equipment vendors, not have to trust anybody, that sounds really good. But you're now asking me and my voters to trust math. And, well, I trust math even less. So I have heard this. But the real important point that's worth making here is that right now, with current election systems, you as a voter have no choice of who to trust. You basically have to trust your local election official. And by proxy, you have to trust the equipment that your local election official has chosen to employ and the equipment vendor. And there's a whole chain of trust that you have no choice in. When you use end-to-end verifiable technologies, then this means that you get to choose who to trust. You can still trust your local election officials if you want, but you can instead proxy your trust to your favorite candidate or your favorite media outlet or any place you want, or not proxy your trust at all and do the checks on your own. You have that choice, and that's a key difference.
And I expect that most people are not going to rent a cluster from Amazon or Azure and run a giant computation. That's not a thing that most people are going to do. But your local newspaper, League of Women Voters, those kinds of organizations can and will do exactly this. I was once having a chat with one of the tech people for one of the large news wires, and I was describing in vague hand-wavy terms how all this stuff works. And I said, so would your organization, spin up a cluster and run these verification things? And he got super excited, like, oh, we would totally do that. And that's an interesting opportunity where a voter might take that receipt thing that they get. We need a better word than receipt, because it isn't actually proof of who you voted for. But if you take that receipt, scan it with your phone, and it gets uploaded into the cloud of League of Women Voters, Democratic Party, Republican Party, local newspaper, Associated Press, and in fact, they can all share with each other because they all know that the receipts are all good. Yeah. Each of those organizations can run the verification process, and if they find a contradiction, if they find something that's wrong, then they might reach back out to you and say, hey, Josh, that receipt that you scanned, do you still have that? And then things start to get really interesting.
Yeah, we've actually tried with limited success in ElectionGuard to get away from the term receipt because it's created some confusion. And I see there's a question in the chat that that is talking about that confusion. The verification code, tracking code, we might call it, that voters receive after voting does not say how you voted. Think of it like a UPS code. It's got a number on it. It's a tracking code, but it doesn't by itself say what's in that delivery that you're getting or what's in that ballot that you have just cast. It allows you to track your ballot to make sure it hasn't been changed. And there is a process having to do with spoiling that I shouldn't use the card trick to show. It's a somewhat subtle process, but that it can be used so that you can be convinced that the contents of that ballot really do represent what your intentions, what your selections were when you voted. But you have no way, when you use one of these systems, of showing anybody how you voted. This would be a very dangerous thing. It would make it easy to sell your vote. It would make it easy for you to be coerced. And we want very much to avoid that. So I want to be as clear as I can in saying that, yes, we are providing voters with a tracking code that you could call a receipt, but if you do call it a receipt, please understand that it does not say how you voted and cannot be used to show anybody else how you voted.
So I think we've addressed, that was Betul Durak's question. I apologize if I don't pronounce your name correctly. But receipt freeness is this very subtle but important property. And it's a property that we see going all the way back to the invention of the Australian ballot, which Josh mentioned in his slides, that if you go to the way elections worked before we had a secret ballot, the fact that you voted for a candidate was well known and enabled bribery and coercion. And so it's really important, and this is a lesson that we learned in the late 1800s, and in fact was central to the women's suffrage movement, is that a secret ballot is essential, and a secret ballot needs to be compelled in the sense that it should not be possible for you to choose to reveal how you voted to anyone. And even if you want to reveal how you voted, you still can't. That idea is an idea that became central to election administration over a century ago. And it's a lesson that we should not give up so soon and so easily.
Yeah, I think that's critical. It's something that is a challenge even in cryptography, because if you look at some of the results of cryptography over the past years, you see, well, you can compute any function you want in a private and secure manner. Great, we have tools to do this. They may not be efficient, but these tools exist. They're not good enough for elections, because those tools, things like secure multi-party computation and other very powerful cryptographic primitives, still allow individuals to show what their inputs are to the function. They don't meet this additional privacy requirement of elections that not only is the privacy of my data, my input, my vote in this case, protected, but I am unable to show anybody else how I voted, even if I wanted. That's a very high standard, and that's a challenge to achieve. But we really do need that level of privacy. If you're a student of American electoral history, you might note that there's a little bit of a blip in the list of American presidents, that the number of presidents doesn't correspond to the number of the president. And that's because of exactly this point, that Grover Cleveland was the 22nd president of the United States. He was elected first in 1884. In 1888, and at that time, we still did not have the secret ballot in the US. In 1888, he was challenged by Benjamin Harrison, and in an election that was seen universally as strife with vote buying, with coercion of various sorts, Benjamin Harrison defeated Grover Cleveland and became the 23rd president of the United States. But because of that experience, the Australian ballot, the secret ballot, swept through the US state by state before the 1892 election. And in 1892, Grover Cleveland again faced Benjamin Harrison. And with the benefit of the secret ballot, Grover Cleveland beat Benjamin Harrison and became president again, and therefore became the 24th president of the United States, even though he'd already been the 22nd president of the United States. And that's why we've got this funniness of, the numbers not quite matching up.
So one of the things that seems interesting about these cryptographic election schemes is that there are so many of them out there. So anybody who's looked at some of the results from the Swiss Post Seidel adventure, there were proofs that turned out to be forgeable. There were a number of things that I guess we could describe as implementation flaws. So is that the sort of reasoning that led you to go with just El Gamal and Sean Peterson, things that are classic, simple, easily understood? Like, did you go out of your way to avoid fancy high-tech stuff? And if you could let just a little bit of high-tech stuff back in, what would you want?
Very much so. Yes, there have been many efforts at better voting systems over the years, especially internet voting systems. And because of recent experiences, many of the purveyors of internet voting systems have said, oh, this end-to-end verifiability seems like an important thing. We should have it. Unfortunately, they often don't understand it very well. Some have been just sort of outright dishonest about claiming they do it when they don't. Some, like the case that you just mentioned here, have genuine, honest efforts to achieve it, but they haven't achieved it. End-to-end verifiability is not an easy tool to build. And the current election vendors in the US especially, but around the world, are focused on other things. They're not typically cryptographic experts. They're trying to get their systems out the door, and they're doing a very good job of what they're doing at times, but they have limitations in what they can do. So that's the genesis of ElectionGuard. We have the ability to make this technology available, and we have gone to some effort to try to make sure that it's done right, it's done simply, it's done in a usable way. And it's really pretty simple for election vendors to use. The approach is basically from the point of view of an election equipment vendor. What you have to do is install the code, and every time you get a vote, whether you're getting it on a scanner or a ballot marking device or wherever it is that you're collecting votes, every time you collect a vote, you call ElectionGuard with the contents of that vote, and ElectionGuard takes care of the encryption and all the necessary aspects of packaging things up, and then just gives you back the verification code to give back to the voter. So we try to make it as simple as possible and as standard as possible, as much as possible, avoiding complexities. There are things that we would like to do to use some slightly fancier things to make things more performant and often simpler for verification. And we're starting to go down that road because performance is critical in many of our applications. So we're offering some slightly more advanced cryptographic techniques, but still being very careful not to go to the bleeding edge on many of these things. We want to have very high confidence that this technology is right, and we're not going to introduce something that's going to fail down the road. Now, still, independent verifiers can check us, but we can still have nightmare scenarios of elections just not completing properly or other things if we don't do this right. So we very much want to be very careful about this and introduce things deliberately.
So this is an interesting question from Etienne Hugo, who asks, what would the additional software and hardware look like to ensure the system as a whole is secure, for example, preventing or minimizing injection of false votes into the ElectionGuard software? So I think we could look at this as a trusted computing-based question. Like, what is the minimum set of things we need to trust in order to have confidence that the outcome of an ElectionGuard election is correct? So do we actually need any of the ElectionGuard code itself, or even any of the computers that voters are touching? Are we requiring that software to be correct, or are we adequately capturing and mitigating if there is malware in a voting machine or in a tabulator?
Yeah, that is a great question. So the ElectionGuard code does not have to be trusted. We are very insistent on this. This is the point of independent verification. You don't have to trust your local election vendors or election officials or Microsoft or ElectionGuard in any way. You can independently verify that the votes have been properly cast, they've been properly recorded, they've been properly counted, that things have been done properly there. But the question does include some important other aspects, because there are some assumptions. We are not getting at all involved in the voter authentication processes. So we are relying strictly on whatever the existing means are of making sure that the voters who come in are eligible to vote, and that only eligible voters are casting votes, and that they cast one vote each, and things like that. The usual procedures of sign-in and counting the number of voters. Now, a lot of the procedures can work very well. For instance, the list of people who voted in an election in the US is generally a matter of public record, and that list can be counted and should correspond to the number of votes that are actually cast. And then people can use the ElectionGuard technology to use their verification codes to say, well, my vote was one of those cast. And everybody who cast a vote can say, my vote was one cast. I see who all the other voters are. And I know that they've had an opportunity to cast their votes and check that their votes have been cast. The example that I gave during the talk actually went a step further and had a name next to every single encrypted vote that has been cast. I think that's a fine way to do things. I'd be happy to do it that way. Most election jurisdictions are very uncomfortable with that and prefer to say, we want that extra layer of indirection. And we want it to be that you can see that your vote is on the list, but there's nobody who's going to be able to look and say, see your name directly and which encrypted vote is attached to you, even though that still provides the protection as long as the encryption lasts. It does, if we go back to the quantum resistance question, make it so that if 20 years later somebody was able to open the record, if there are names associated with those ballots, then they could see 20 years later who voted how. So it is kind of nice to be able to say, okay, we'll have this indirection. There's a list of voters and there's a list of votes, and we know that everybody can check the association, but you can't specifically check whose vote, even encrypted form, corresponds to who.
Now, there's one interesting twist on this, which is a question that's often described as hand-marked versus machine-marked paper ballots. And the gist of this is consider two alternative voting systems, no fancy cryptography at all. Voting system one, we have human beings who mark paper by hand, and then it's machine scanned. Version two, you have a touchscreen computer of some sort, and you select your candidates and you hit print, and then it prints a ballot. The printed ballot, the hand-marked ballot look exactly the same bubbles in the same places. So that's the setup. So in a world where you have a computer assisting you in the production of that paper ballot, sometimes called a ballot marking device, there's a concern that malware in the computer might show you, the human being, one thing while printing something different. And even on a printed paper ballot, it might you might vote President Alice, and it might print out President Bob instead of Alice. And that's something that it can print a completely consistent ballot. It can compute the ElectionGuard encryption in a consistent way. It just differs from the voter's intent. This is an interesting challenge, but it's also an eminently auditable and mitigatable problem. So you can imagine human auditors going through the voting process, just like regular voters, and election officials know that auditors don't get to put ballots in the ballot box, but they get to play with the machine. So an auditor could play with the machine in a prescribed way, enter test votes that had better come out correct, and that would be, and since the machine can't tell whether it's a real voter versus an audit voter, that's a way that you might be able to catch machines if they're cheating. That and other processes like it can help us mitigate against the increased risk of malware when it's in the loop of the voter entering their vote preferences.
Yeah, and because we're running out of time, I'm going to punt any detailed answer to some other opportunity. But I will say that one thing we've tried hard to do with ElectionGuard is stay neutral on this. Many people prefer hand-marked paper ballots for many reasons. ElectionGuard is perfectly capable of working in systems with hand-marked paper ballots. There are many reasons why some voters can't use hand-marked paper ballots and have preferences for ballot marking devices. ElectionGuard works there as well. We are trying to stay out of those questions and concerns and make ElectionGuard available to be used however a local jurisdiction prefers to use it.
Yep, and one of the cool parts about ElectionGuard is the core library is a bunch of low-level crypto primitives, and then above that, there are election abstractions like ballots, and then above that, there are abstractions like tallies. And so the layers of the ElectionGuard software allow themselves to be easily adapted to these different use cases.
Yeah, it's designed to be flexible and open source so that you can adapt it as you wish, or we're happy as Microsoft and Dan to work with you and try to see what your use cases may be. and learn and make adaptations.
And not just open source, it's also open spec. So all the specs are written down with all of the equations, and in many cases, I typed the equations in and they worked. In one case, I typed the equation in and found a counterexample, and I'm like, hey, Josh, I don't think this exponent is right. And we're reasonably confident now that the spec and the implementation are all doing the right thing.
Indeed, indeed. So thanks, everybody. I hope that we've answered all of your questions, and please feel free to contact me or Dan, I presume, if you want to learn more. And we're happy to continue answering questions, and hope that you'll be interested in using this technology and maybe even have a chance to vote with this technology in coming years.
Thank you all for joining us. It was a real pleasure.
Bye all.